Alright, hey guys, Titmus here. Today we're going to learn how to understand velocity versus time graphs and use them to create position versus time graphs, okay? So here's the scenario I want you to imagine. We've got ourselves a squirrel right here. You can see Mr. Squirrel right there. And our squirrel, he's running with his acorn. He's going to try and get up a tree. And all of a sudden a dog comes out, and the squirrel runs back, and then realizes that the dog's on a leash and can't get him. So he goes towards the tree, maybe a little bit more slowly, but he's going to go back towards the tree and climb up his tree and hide his acorn. Okay, so that's the scenario. And this right here is the position versus time graph for that scenario, right? And what we're going to do is we're just going to refresh how to turn that into a velocity versus time graph, okay? Now, what you should be familiar with, this should be a review, but you should know that the slope of a position time graph gives us the velocity time graph, right? And why is that? Well, let's bring it back to what we know about velocity, right? We know that average velocity is equal to your displacement, your change in position, divided by the time. And if we take a look at this graph, the displacement is really given by the vertical axis, and the time is given by the horizontal axis. And so the displacement is the rise, the vertical part, and the time is the run, or the horizontal part. And from that, rise over run we know is slope. So out of all of this, what we really get is that average velocity is slope when we look at a position versus time graph, okay? And so we can look at that and we see, okay, we've got ourselves a slope here of 5, and so on the velocity graph for the same amount of time, the velocity graph will read 5. Here we have a slope of negative 10, and so on the velocity graph we get negative 10. And here we've got a slope of 2.5, and so the velocity graph reads 2.5. Okay? So now the question is, how do we reverse that process, right? How do we get from a velocity graph back to a position graph? And maybe the easiest way is to just say, well, let's reverse the process. If the slope of a position graph gives us the velocity graph, then the velocity graph should tell us the slope of the position graph. Okay? And so let's try that out. I've taken this velocity graph here, and I've just copied it down here. That's the exact same velocity graph. And so we're going to use that and see if we can create a position graph that looks the same as it used to. Okay, so looking at the velocity graph, here is our velocity. It says that the velocity is 5, and that means that the slope of our position graph should be 5. Okay, so a slope of 5 means that I start here at the origin and I go up 5 over 1, up 5 over 1, up 5 over 1, up 5 over 1, right? If I were to continue that line, it would go all the way out here, but we only need to continue it for the same amount of time that the velocity holds that amount, right? So the velocity is 5 right here until 4 seconds, so we stop our line right there at 4 seconds. Okay. The next segment on our velocity graph has a slope of negative 10, and so our slope now should be negative 10. And so we can draw that in. We start at the same place where we left off, and we go down 10 over 1, down 10 over 1, down 10 over 1. But again, we want to drag it back and keep it only as long as it needs to be, right? This segment only lasts for 1 second, so this segment only lasts for 1 second. And then finally, we've got ourselves a segment here of a velocity of 2.5. So our slope should be 2.5. So we just take this and we draw a line, 2.5 over 1, 2.5 over 1, 2.5 over 1, so on and so on, until we've matched the ending time right there and there. Okay? So we've drawn ourselves a position graph. The question now is, does it look the same as it did before? Okay? And so all I'm going to do, and I get to cheat a little bit because I've got a fancy digital tool, I'm just going to cut out the graph bit and I'm going to move it, and lo and behold, you should see that it sits over the top of that red line perfectly. It's the exact same graph, okay? So it works. The velocity graph does tell us the slope of the position graph. We can work it backwards. Excellent. Let's look at the second way, because while that way works, pretty soon it's not going to be very useful. And so I want to show you something that's going to be a little bit more versatile. And for that, we've got to go back to our equation. Okay? We know that average velocity is displacement divided by time. Now, if we rework that equation a little bit, we get that displacement is equal to average velocity times time. Okay? Now, if we look at that on our velocity graph, here's what we see. We see that the average velocity, the velocity is read on the vertical part of the graph, and the time is read on the horizontal part of the graph. And if I multiply the vertical bit with the horizontal bit, that's like talking about a rectangle. And that's like calculating the area of a rectangle. So can I do that? Can I just multiply the height and the width like an area and use that to figure out displacement? Let's find out. Let's see if it works. Right? It's promising. So, again, same velocity graph right here as we had before. I've got myself a blank position graph. We're going to see if we can create the same position graph. So we're going to look here and figure out what is the area of this graph. Now when I talk about the area of the graph, we're talking about the space between the line of the graph and the axis, and we draw vertical lines in to bound that region off. Okay, so that's what we're going to draw, and now I need to figure out the area of that graph. Well, the length of this box is 4. How tall is the box? You might think that it's 2, because we've got 2 boxes, right? But here's where we need to look at the scale. The scale shows us that the height there is actually 5. Okay? And so then we've got a rectangle that's 4 long by 5 high, and 4 times 5 is 20. Okay? So the area of this box is 20. 20, what, 20 square feet? No. The units are units of meters per second multiplied by units of second. Meters divided by seconds times seconds, well, that's just meters. So the units of the area is just 20 meters, which doesn't sound like an area. I know, just go with it. But here's how we do it. We got that the area is 20, so now we can draw a line that starts at 0 and goes up to 20. Okay? So now let's look at the second part of the velocity graph here. The next part is this section down here. And this section has a width of 1 second and a height of -10 meters per second. -10 times 1 is just -10. So that has an area of -10. Now, what some people think this might mean is that I've got to go from there all the way down to negative 10. But that's not the right way to interpret it. What we really need to do is just go 10 down from where we were. We need to go negative 10 from where we were. So we were here, and we're going to go 10 back. We were at 20, now we're at 10, right? We subtracted 10 from 20. And then finally, we can look at our last little rectangle here. And this one has a length of 6 and a height of 2.5. And 2.5 times 6 is 15. Right? So this last rectangle has an area of 15, and so from here I'm just going to draw a line that goes up 15, like so. And I think we can see by looking at this graph and looking at this graph that those are identical. So it works. If we look at the area of the velocity graph, we can get the position graph. Fantastic. Okay, let's do one more example so that you guys can see if you get it. So here is another velocity graph that I've given you. Okay, and what we're going to do, we're going to turn that into the position graph. But I'm going to give you guys a chance to figure it out. So go ahead and pause the video, draw a sketch of your position graph, and then when you're done, resume the video and you can compare your answer to mine. Okay? Alright, pause the video now. Alright, so you did it. You made a position versus time graph. Let's see if you made it the same way as me. So, we're going to come down here, and I'm going to do this using the area method, because the area method is just a little bit better. So, we've got ourselves a rectangle here. The width is 2, the height is 10, 2 times 10, that's an area of 20. So, starting from 0, in those 2 seconds, I go up to 20. Okay? And then the next area is an area of 2 times 5. It's 5 high, 2 wide. That's an area of 10. Now, the mistake that many people might make is by going from 20 to 10. Keep in mind, that's not what we're doing. We're actually adding 10 to our position. So we were at 20, add 10 to that, we got to go up to 30. Okay? Now this next segment's a little bit weird. How tall is the rectangle that I draw between the red line and the axis? Well, the red line's on the axis. So there is no rectangle. It has no height. There's no area. That means that I don't go anywhere. My position is at 30 and it stays at 30. Okay, so I get a flat line there. And then finally, I can look at this section, and my width there is 4 seconds, and my height is negative 10. 4 times negative 10 is negative 40. And so I've got to go 40 meters down from where I was. So I start at 30 and I go down. Is it going to snap? Oh, I didn't draw that well enough. Okay, down to 40. Boom. Okay. Down by 40, that takes me to... Oh, hang on. Oh, I've messed up. Look, my graph goes below the axis, and I didn't draw in an axis for it. This graph is no good. It's okay. This is going to happen sometimes. When you go to draw graphs, if you haven't planned ahead, which sometimes planning ahead is really hard, you're going to end up drawing your graph off of the axes. It's fine. All you've got to do is just draw another graph. So we're just going to come down here. I've made a new set of axes. It's a little bit bigger now so that we can get everything in, and we'll just draw it all again. That's fine. We'll go to 20, oops, and then we'll go to 30, and then we'll stay at 30, and then we'll go down to negative 10. And there is our completed graph. That is hopefully what you ended up drawing. Okay? I hope this all makes sense. If you have any questions, feel free to reach out and I'll help you. All right, you guys have a great day.